The 3.8-Billion-Year Design Lab: How Sharks, Birds, and Termites Are Teaching Engineers. On a quiet morning in Japan, a sleek bullet train exploded from a tunnel at nearly 200 miles per hour. Passengers barely noticed. People living nearby did. Every time the train burst from a tunnel, it produced a thunderous sonic boom. Engineers spent years trying to solve the problem. They tested materials, modified engines, and redesigned components. Yet nothing worked well enough. Then one engineer looked away from the laboratory and toward a riverbank. There he saw a kingfisher. The small bird plunged from the air into water with astonishing precision, barely creating a splash as it crossed from one environment to another. The engineer wondered, what if a train could move from tunnel to open air the same way? The front of the Shinkansen bullet train was redesigned to mimic the shape of the kingfisher's beak. The results were remarkable. The train cut through the air efficiently enough to allow 10% faster potential speeds, while using 15% less electricity. Even more importantly, the sonic boom nearly disappeared. A problem that had frustrated some of the world's best engineers was solved by a bird. That is the power of biomimicry. Nature, the world's greatest engineer. Biomimicry is the practice of learning from nature's designs and applying them to human challenges. The idea is surprisingly simple. Every organism alive today represents a solution that has survived millions of years of testing. Over roughly 3.8 billion years, evolution has conducted the longest and most rigorous research and development program in history. Nature has experimented with flight, cooling systems, water management, construction materials, communication networks, and energy efficiency. Long before humans ever built cities or computers. When a design fails in nature, it disappears. When it succeeds, it survives. That means every feather, leaf, shell, and spiderweb contains lessons refined through countless generations. Biomimicry pioneer Janine Benyus famously encouraged us to view nature as a model, a measure, and a mentor. The question is no longer, what can we take from nature? It is becoming, what can we learn from it? The bird that changed the world. One of the most famous examples of biomimicry began during a walk. In 1941, Swiss engineer Georges de Mestral returned home after hiking with his dog through the Alps. Both were covered in stubborn burrs. Annoyed but curious, he examined the burrs under a microscope. What he discovered changed everyday life. Each burr was covered with tiny hooks that latched onto loops in fabric and animal fur. Nature had created a fastening system that was strong, reusable, and remarkably efficient. De Mestral spent years refining the idea. The result became Velcro. Today, Velcro appears in shoes, clothing, medical devices, spacecraft, and thousands of products around the world. What looked like a nuisance in the countryside turned out to be a brilliant engineering solution hiding in plain sight. The building that breathes. Imagine a large office complex in Africa that stays cool without relying heavily on air conditioning. It sounds impossible. Yet the Eastgate Center in Harare, Zimbabwe, does exactly that. Its inspiration came from termites. In the African savanna, termites build towering mounds that maintain stable internal temperatures despite scorching days and cool nights. Inside these structures, an intricate system of tunnels constantly circulates air, removing heat and regulating humidity. Architect Mick Pierce realized that buildings could do something similar. The Eastgate Center uses natural ventilation and passive cooling inspired by termite mounds. As air moves through the structure, heat is removed without requiring massive amounts of electricity. The result is extraordinary. The building uses roughly 90% less energy for ventilation and cooling than comparable conventional buildings. In its early years, it saved more than $3.5 million in air conditioning costs. Sometimes the future of architecture looks surprisingly similar to a pile of dirt built by insects. The shark that taught airplanes to swim. Most people assume smooth surfaces move fastest through water and air. Sharks prove otherwise. A shark's skin is covered with microscopic V-shaped ridges called dermal denticles. These tiny structures reduce drag and discourage bacteria and parasites from attaching to the surface. Engineers studying sharks realized something astonishing. The same texture that helps sharks glide efficiently through water could also help airplanes move more efficiently through air. This discovery led to AeroShark, a special film applied to sections of commercial aircraft. The film reproduces the microscopic texture of sharkskin across portions of an airplane's fuselage and engines. The impact may seem small at first. Drag is reduced by roughly 1%. But in aviation, 1% is enormous. A single Boeing 777 equipped with this shark-inspired technology can save approximately 400 tons of jet fuel, while preventing more than 1,200 tons of carbon dioxide emissions every year. A predator that evolved in Earth's oceans hundreds of millions of years ago is now helping reduce emissions in the skies. Lessons from leaves, whales, and desert beetles. Nature's ingenuity appears in places many people never think to look. Consider the lotus leaf. Lotus flowers grow in muddy ponds, yet their leaves remain remarkably clean. Scientists discovered that microscopic bumps on the leaf create a highly water-repellent surface. Water droplets roll away like tiny cleaning machines, carrying dirt and dust with them. This phenomenon, known as the lotus effect, inspired self-cleaning paints, glass, textiles, and coatings. Buildings coated with lotus-inspired materials can reduce cleaning and maintenance costs by as much as 50%, while reducing the need for harsh chemical cleaners. Then there are humpback whales. Despite weighing up to 40 tons, these giants are surprisingly agile swimmers. Scientists discovered that bumps along the leading edge of their flippers improve water flow and reduce drag. Engineers copied this design for wind turbine blades. The result was improved efficiency and better performance at lower wind speeds. And in one of Earth's driest places, the Namib desert beetle survives by collecting water from fog. Its shell combines water-attracting and water-repelling surfaces that gather tiny droplets and guide them directly toward the insect's mouth. Today, engineers are applying the same principles to water harvesting systems, helping communities capture fresh water from the atmosphere. A flower, a whale, and a beetle all offer solutions to challenges facing modern civilization. The brainless designer. Perhaps the most astonishing biomimicry story involves a creature with no brain at all. Slime mold is a simple organism that spreads across surfaces searching for food. To most people, it looks like little more than a strange patch of living goo. Scientists in Japan, however, suspected it might have something to teach them about efficiency. To test their idea, researchers created a miniature model of the Tokyo region. They placed oat flakes on a flat surface, with each oat flake representing a major city around Tokyo. Then they placed a small piece of slime mold at the location representing Tokyo itself. The slime mold began doing what it always does, searching for food. As it spread outward toward the oat flakes, it formed a network of thin tubes connecting the food sources. At first, the network was messy and full of redundant pathways. But over time, the organism gradually abandoned inefficient routes and strengthened the most useful ones. The final pattern surprised the researchers. When they compared the slime mold's network with Tokyo's actual railway system, they found a striking similarity. Both networks connected major population centers efficiently while maintaining alternative routes. In case one pathway failed, human engineers had spent decades designing and refining Tokyo's transportation network. The slime mold arrived at a remarkably similar solution in just a few days. What makes this achievement so remarkable is that slime mold has no brain, no nervous system, and no central control. Its only objective is to find food while using as little energy as possible. Yet that simple goal led to a solution resembling one of the world's most sophisticated transportation systems. Today, researchers study slime mold to improve everything from traffic flow and logistics networks to urban planning. Sometimes intelligence does not require a brain. Healing without stitches. Not all biomimicry involves buildings, trains, or transportation. Some of the most exciting breakthroughs are happening in medicine. Surgeons have long faced a difficult challenge: repairing wet, moving tissues inside the human body. Traditional adhesives often fail because organs are slippery, flexible, and constantly in motion. Engineers searching for answers turn to an unlikely source: a slug. When threatened, the dusky Aryan slug secretes a defensive mucus that is extraordinarily sticky, flexible, and non-toxic. The mucus remains attached even in wet conditions. Biomedical researchers studied the slug's chemistry and created a new type of surgical adhesive based on the same principles. The resulting hydrogel can bond to wet tissue and remain flexible as organs move. In laboratory testing, similar materials successfully sealed holes in beating pig heart tissue without the need for stitches. Nature was performing advanced chemistry long before humans built factories. Beyond copying nature. Many people think biomimicry is simply copying shapes. But the field is evolving far beyond that. Experts often describe 3 levels of biomimicry. The first level imitates form, such as the kingfisher's beak or the lotus leaf. The second imitates process, such as the slug-inspired medical adhesive. The third imitates entire ecosystems. Forests produce no waste. One organism's leftovers become another's resources. Nutrients cycle continuously through the system. Modern industries are beginning to apply the same philosophy. Instead of the traditional extract, manufacture, use, and discard model, companies are exploring circular systems, where materials are continually reused and regenerated. Nature does not simply create products. It creates relationships. That may be its greatest lesson of all. When artificial intelligence meets evolution. The next chapter of biomimicry may involve a partnership between nature and artificial intelligence. For centuries, scientists had to observe nature one species at a time. Today, AI can analyze thousands of biological structures simultaneously. Researchers are feeding evolutionary data into advanced algorithms capable of discovering patterns humans might never notice. Instead of spending years studying a birdwing or a whale flipper, engineers can use AI to compare millions of natural designs in days. The resulting blueprints often resemble nature itself. Some lightweight vehicle components now mimic the internal lattice structures of bird bones. Other AI-generated designs resemble coral skeletons, tree roots, or honeycombs. These structures use less material while maintaining extraordinary strength. In a sense, engineers are no longer merely copying nature. They're collaborating with it. The future is already here. For centuries, humanity believed progress meant conquering nature. Today, a different vision is emerging. The fastest trains borrow ideas from birds. Skyscrapers learn from termites. Airplanes imitate sharks. Medical adhesives mimic slugs. Computer algorithms study slime molds. And artificial intelligence searches the natural world for solutions to challenges we have not yet solved. The future may not belong to technologies that separate us from nature. It may belong to technologies that understand it. After all, nature has already spent 3.8 billion years perfecting its designs. The greatest innovation of the 21st century may simply be learning to pay attention.
It's time to study new words in context. 1. Sleek. Definition: smooth, modern, and attractive in appearance. Example: the sleek train moved quietly through the station. 2. Sonic boom. Definition: a very loud noise made when something travels faster than the speed of sound. Example: The jet created a sonic boom as it flew across the sky. 3. Component. Definition. A part of something larger. Example. The engine is an important component of a car. 4. Plunged. Definition. Moved or fell quickly into something. Example. The bird plunged into the water to catch a fish. 5. Mimic. Definition. To copy or act like something. Example. Engineers tried to mimic the shape of a bird's beak. 6. Biomimicry. Definition. The practice of copying ideas from nature to solve human problems. Example. Biomimicry helped engineers design a better train. 7. Rigorous. Definition. Very careful, thorough, and demanding. Example. Scientists carried out rigorous testing before using the new design. 8. Latched. Definition. Attached or held on tightly. Example. The burr latched onto the dog's fur. 9. Nuisance. Definition. Something that is annoying or causes trouble. Example. The loud noise became a nuisance for nearby residents. 10. Scorching. Definition. Extremely hot. Example. People stayed indoors during the scorching summer day. 11. Intricate. Definition. Having many small parts or details. Example. The insect built an intricate network of tunnels. 12. Dermal. Definition. Related to the skin. Example. Sharks have special dermal structures on their skin. 13. Denticles. Definition. Tiny, tooth-like scales made of enamel and dentin that cover a shark's skin to reduce friction and drag. Example. Shark denticles help reduce drag in the water. 14. Predator. Definition. An animal that hunts and eats other animals. Example. The shark is a powerful predator of the ocean. 15. Ingenuity. Definition. The ability to create clever and useful ideas. Example. The invention showed great human ingenuity. 16. Water repellent. Definition. Able to keep water from sticking to a surface. Example. The jacket is water repellent and stays dry in the rain. 17. Agile. Definition. Able to move quickly and easily. Example. The whale was surprisingly agile in the water. 18. Goo. Definition. A thick, sticky, soft substance. Example. The child touched a strange green goo on the table. 19. Redundant. Definition. Not needed because something similar already exists. Example. The workers removed redundant steps from the process. 20. Logistics. Definition. The planning and movement of people, goods, or supplies. Example. Good logistics help the company deliver products on time. 21. Urban planning. Definition. The process of designing and organizing towns and cities. Example. Urban planning helps make cities safer and more efficient. 22. Adhesives. Definition. Substances used to stick things together. Example. Strong adhesives are used in construction projects. 23. Mucus. Definition. A slippery substance made by people and animals. Example. The slug covered itself with mucus for protection. 24. Hydrogel. Definition. A soft material that contains a large amount of water. Example. Doctors used a hydrogel to help repair damaged tissue. 25. Beating. Definition. Moving with a regular pumping action, like a heart. Example. The doctors could see the beating heart during the test. 26. Simultaneously. Definition. At the same time. Example. The two machines started working simultaneously. 27. Lattice. Definition. A structure made of connected strips or parts that form a pattern. Example. The bridge used a lattice design to make it strong.
Comprehension questions. 1. What problem did the Japanese bullet train create when it came out of tunnels? Answer. It created a loud sonic boom that disturbed people living nearby. 2. What animal inspired engineers to redesign the front of the Shinkansen bullet train? Answer. The kingfisher inspired the redesign. 3. How did the kingfisher-inspired design improve the train? Answer. It allowed faster potential speeds, reduced electricity use by 15%, and greatly reduced the sonic boom. 4. What is biomimicry? Answer. Biomimicry is the practice of learning from nature's designs and using those ideas to solve human problems. 5. Why is nature often called the world's greatest engineer in the article? Answer: because nature has been testing and improving designs through evolution for about 3.8 billion years. 6. How did George de Mestral get the idea for Velcro? Answer: he noticed burrs sticking to his clothes and his dog's fur and studied them under a microscope. 7. What feature of burrs inspired the invention of Velcro? Answer: their tiny hooks that latch onto loops in fabric and fur inspired Velcro's fastening system. 8. What natural structure inspired the design of the Eastgate Center in Zimbabwe? Answer: termite mounds inspired the building's cooling and ventilation system. 9. How much less energy does the Eastgate Center use for cooling and ventilation compared to similar buildings? Answer: it uses about 90% less energy. 10. What are dermal denticles and where are they found? Answer: dermal denticles are tiny tooth-like structures found on a shark's skin. 11. How does shark-inspired aeroshark technology help airplanes? Answer: it reduces drag, saves fuel, and lowers carbon dioxide emissions. 12. What is the lotus effect? Answer: it is the ability of lotus leaves to stay clean, because water rolls off their surfaces and carries dirt away. 13. How have engineers used ideas from humpback whales and desert beetles? Answer: whale flippers inspired more efficient wind turbine blades, and desert beetles inspired water harvesting systems. 14. What experiment did scientists perform with slime mold? Answer: they placed oat flakes to represent cities around Tokyo, and observed how slime mold connected them with efficient pathways. 15. Why was the slime mold experiment so surprising? Answer: the slime mold created a network similar to Tokyo's railway system, even though it has no brain or nervous system. 16. What natural substance inspired a new type of surgical adhesive? Answer: the defensive mucus produced by the dusky Aryan slug inspired the adhesive. 17. What advantage does the slug-inspired hydrogel adhesive have? Answer: it can stick to wet moving tissue and remain flexible. 18. What are the 3 levels of biomimicry discussed in the article? Answer: they are form shape, process how something works, and ecosystem how systems interact. 19. How is artificial intelligence helping biomimicry today? Answer: AI can analyze thousands of biological designs and help engineers discover new solutions inspired by nature. 20. What is the main message of the article? Answer: the article shows that nature's designs can inspire better technologies, and that learning from nature may help solve many future challenges.